Hi and welcome everybody to the lecture titled Angle Modulation, the second part related to angle modulation. And this lecture is part of a series of lectures related to Introduction to Communication course. In the previous lecture, we introduced angle modulation, which is different from amplitude modulation. We explained the phase modulation and the frequency modulation, and discuss the mathematical formula of each one of them and the relationship between them, and we gave some examples of how to modulate the signals using frequency modulation and phase modulation. And we said they are suitable for certain applications that amplitude modulation is not good for. In today's lecture, in this lecture, we will be discussing mainly the bandwidth of the frequency modulation using Carlos rules, and then the spectrum analysis of frequency modulation, and particularly we'll move and discuss about narrowband frequency modulation and wideband frequency modulation. So a little bit, the lecture is going to be heavy in math, technically deep a little bit more than the previous lectures, so you have to a little bit give us your attention and your focus more so that you understand what we are saying and what we are doing in this lecture. So angle modulation, as we have shown you in the previous part, in the previous lecture related to angle modulation, is non-linear, not like amplitude modulation, linear modulation scheme, linear modulation process. It's non-linear and it's really complex to analyze, not so easy. And especially when you are required to analyze the bandwidth of the modulation. The bandwidth can really can have infinite bandwidth. So there are two approximations for FM in general. If we want to study FM, there are two approximations and we need to study both of them and take care of them. The first approximation, we call it narrowband frequency modulation, and the second one wideband approximation. Now for the narrowband frequency modulation, in this case the bandwidth is narrow and you can find it to be small, while wideband approximation, you approximate your modulation scheme, angle modulation, to wideband scenario, and in this case the bandwidth is a little bit large. And you will see that the bandwidth of angle modulation or frequency modulation in general is sometimes infinite, but as the frequency increases, the power of those high frequency harmonics becomes so little that you can ignore it, and that's why you can confine the bandwidth. You can say that the bandwidth can be approximated to certain value. So having said this, let's assume that A of t is basically the integration of the message signal. Yes, the integration of the message signal, and let's assume that kf, which is the factor associated with the frequency modulation, multiplied by the amplitude, multiplied by A of t, which is the integration of the message, take the amplitude, and we assume that this value is much smaller than 1. Then the signal bandwidth, your modulated signal, can be approximated to be equal to 2 bm, where bm is the bandwidth of the message itself. So this is similar kind of to double sideband suppressed carrier modulation. The bandwidth of the modulated signal is equal to 2 bm. If bm is for the message, then the total bandwidth of the modulated signal is this. Now when you have narrowband frequency modulation, the mathematical formula of the frequency modulated signal is given as follows. It's equal to alpha cosine omega ct minus kf alpha t sine omega ct. Now this is the approximation we are talking about. You remember alpha is basically the integration of the message. so that when you derive it and you try to find the instantaneous frequency in frequency modulation, the instantaneous frequency changes directly with the message signal without any derivative, without anything. And sine omega ct is coming from the approximation. So the difference between the previous equation we explained in the previous part of the lecture related to angle modulation and this equation is the fact that we are adding this sine omega ct. This is for approximation, and this we already know alpha t integration of m of u, and this is frequency modulation, not phase modulation. Now this is for narrow band. These are the conditions that magnitude of kf a of t is much smaller than 1. For wideband frequency modulation, the frequency deviation delta f is equal to maximum amplitude of kf multiplied by m of t, and we call this peak frequency deviation. In that case, the bandwidth is given by this formula. Compare this now to this. Can you see the difference? They are not equal. In narrow band, the signal bandwidth is almost similar to the amplitude modulation bandwidth, to double the frequency, double the message signal bandwidth, while in wideband frequency modulation you have the factor of 2 delta f. Delta f is the peak frequency deviation. You add it to 2 bm. This is known in the literature as Carson's rule. Now let's look into it in more depth, this Carson's rule, and how is it related to the bandwidth of a frequency modulated signal. So let A of t, as we assumed, is equal to the integration of the message m of u delta u, and let us define the complex frequency modulation signal by exponential instead of cosine. Yes, you remember with me that e to j something, anything, is equal to cosine plus j sine. Yes, you remember this. Now, in the previous equation, we wrote the modulated signal in terms of cosine. Now, let's write it in terms of exponential. So, the modulated frequency signal, phi of t for the FM modulated signal is equal to A, which is the amplitude, e to power j omega ct kf alpha A of t, which is the integration of the message. And this, as we know from math, since there is plus sign, you can take two factors, e to j kf alpha A of t, and multiplied by e to j omega ct. If you take the real part, then you will end up having something like this using the power series. You know the analysis, the power series, I don't know if you have taken it in math, but for the ones who don't know, if you have an exponential function like this, e to j kf A of t, you can approximate this function using the power series analysis. So basically, you can write, instead of writing this function that can go to infinity, you write it, you take only few terms at the beginning and you say that these three terms represent this function. But in general, the series, this function, this one, yes, don't get afraid of this. It's not scary. You just, this is equal to this. This function, let me again buy a different color so that you understand this. You take this exponential, any exponential function can be expanded using power series expansion method. And this can be written in this format. The goal here is to just take few terms that can represent the whole signal. So this A to JKF A of t can be written as 1 plus JKF A of t plus, but as you can see, basically you remove the exponential thing. You make it summation and multiplication only to make it easy to analyze it and process it and find the closed form formulas for your modulation scheme. If A of t, which is the integration of the message, has a bandwidth equal to 2b hertz, then the nth term here, nth term, this is zero term, this is first term, second term, nth term, this is nth term, yes? Nth term, if I ask you to find the bandwidth of this nth term, which is you take the message signal, you make it to power n and you multiply it by kf to power n factorial j to power n. The bandwidth of this term, if I ask you find this bandwidth, you basically multiply it by n. Take the bandwidth of the signal and multiply it by n. This expansion shows that the bandwidth is infinite. Infinite, it can goes to infinity. If the bandwidth of this is 2b. The bandwidth of this is 2 multiplied by 2b. And then after the one after it, 3 multiplied by 2b. And this n multiplied by 2b. This expansion goes to infinity. And this means that the bandwidth as well, if you were asked to find the whole bandwidth, then the bandwidth would go to infinity as well. So what does this mean? I mean, this is bad. We don't like the bandwidth of our modulated signal to go to infinity, because if it goes to infinity, then we would need to occupy the whole spectrum, means to use the whole spectrum. And we already know that the spectrum is very precious resource. We cannot waste it. We must use it effectively and wisely. We must have to make the best use of it, because we buy it from the governments and we pay $millions of dollars. So how come we can use this narrowband? How come we can use this frequency modulation scheme to modulate and send our signal if it occupies the whole bandwidth? It will interfere with the other guys, with the other companies, and they will complain about us and go to the court and say that we are interfering with them, and they might fine us, and this is problematic for us. So we must make sure that it doesn't interfere with everybody else who's doing his own business with his own frequencies. So when we look into this mathematically, we find out that these high terms here, which are part of the expansion method, the bandwidth, as you increase the term number, the bandwidth increases, yes, because n increases. For example, when n goes to 100, it's not like when n equal 1. When equal 1, it's 2b. When equal goes to 100, 2 multiplied by 100, 200b is so massive, so huge, nobody can afford it. However, when you find the power, when you try to find the power of that signal with this bandwidth, you find out that the power is almost close to zero. So imagine your signal has this bandwidth, but the power is the power of that signal is this. So it's almost close to zero. It's insignificant. Since the power is so small, it doesn't cause interference to the other signals generated by the other companies or the other FM station. Everybody operates normally. So therefore we can ignore these high terms and just take few terms, maybe these ones, these two, the first two ones, and ignore the remaining ones, because mathematically when you increase n and find the value of kf to power n over the factorial of n, you find out that as n increases, this goes to zero ultimately. And this means that all these terms, I can remove them and just take few terms at the beginning, and those will represent my signal. Isn't it beautiful? It is, because it simplifies our life and makes this modulation scheme practical. Otherwise, if it occupies the whole bandwidth and this whole bandwidth has really a significant amount of power, then we cannot use it practically, as it will interfere with the other guys who are using their frequencies to provide other services. So if you understood this, now things becomes very easy for you to analyze and find the bandwidth exactly for the modulation scheme we are looking into. So when you take the real part, yes, I said here you take the real part. The real part is basically, since you are talking about exponential function e to power j something is equal to cosine that thing plus j sine. Real means without j, so you basically convert this into cosine. So here, instead of this equation, you put what? You put this cosine omega ct plus kf alpha t sine omega ct plus this cosine. Basically, we removed the exponential. Now, for the case when kf alpha a of t is much smaller than 1, then all but first two terms are negligible. This means that you can get rid of all these terms, because this value is so small. When you find these values under this condition, you will find out that this value is 0. This value is 0. You will be only left with these two terms, and the narrowband FM approximation in this case can be written in this equation. This is the narrowband FM approximation. It's basically cosine omega ct plus minus kf a of t sine omega ct. Imagine all this mess, all this very lengthy equation that it goes to infinity. We don't know when will it stop. If we have this condition satisfied, we can rewrite this equation in this form. Simple, two terms. You just take these two things, put them here, and this is your narrowband frequency modulated signal, and you get rid of these because these goes to 0 mathematically. Although they have bandwidth, the bandwidth is, for example, for this, the bandwidth is 2 multiplied by 2b, and the bandwidth here is 3. For this, 3 multiplied by 2b. But the good thing that the power of those terms goes to 0. Then I can get rid of them, and at the end of the day, I will have only these two terms that have significant power. Now, what's the bandwidth of these two terms? 2b. Same as the bandwidth of AM. Narrowband frequency modulation has power of half a square, which does not depend directly on M of t. Why it doesn't depend directly on M of t? Because you don't change it based on the, you don't change the amplitude here based on the message signal. You change the phase or the frequency based on the message signal. Now, this is for a frequency modulation. Yes, FM. This is FM. If I ask you to find phase modulation, we know that phase and the frequency, they are related to each other. And the narrowband approximation in this case, it's basically what's the key difference between phase and frequency? In phase modulation, we modulate the signal frequency with respect to the message signal directly, without integration, without anything. But here, you modulate it based on the integral of M of t, because you want the instantaneous frequency to change with the signal, with the message signal directly in frequency modulation. But here it changes with the derivative of the message. So these are the key differences. So this is for this equation for phase modulation, and this equation for frequency modulation and narrowband. Narrowband, don't forget this. Narrowband, when I say narrowband, this means that this condition is satisfied and I can simplify this long equation in these two terms only. And this is for frequency modulation, where the signal frequency, the modulated signal, is changing with the integration of the message alpha t. A of t is basically the integration of m of t as we defined it, and in phase modulation it changes directly with the m of t. So this is now clear. We understand that, and we understand that the bandwidth of narrowband signal is 2b, and the power is half a square, which is similar to amplitude modulation, kind of, but you are not changing the amplitude. Now, let's say now we play with this factor. For narrowband, we said it's much smaller than 1. Let's play with this factor and make it somehow close to 1, near 1, and greater than 1. Fc is equal to 20, Fm is equal to 1. And see the changes. As you increase this factor, somehow the signal in time looks similar, but actually the oscillations here increase. The oscillations increase a little bit more, but in time it's difficult to see the difference. But when you go to the frequency, you will see that when kf multiplied by a of t and take the absolute value is equal to 0.2, you have only these components, 3 on the left, 3 on the right, and you have these little, very little, you can ignore them even. When you increase this value to 0.8, you can see that new components start to appear, and the previous components get a little bit larger. Means that the bandwidth of your signal increases as you increase this value. Now let's take the value 3.2. 3.2, you get this shape on the right and this shape on the left. And this is really large. The bandwidth here, as you can see, is from this point to this point, and we have multiple components, multiple frequency components appearing. And the power of these components is increasing. So this means that the bandwidth for when this condition is not satisfied, we cannot consider the frequency modulation narrowband anymore. It's wideband, and the bandwidth is increasing a little bit more and more. So what does this mean? For wideband frequency modulation, the frequency deviation contributes to the FM bandwidth. In this case, the FM signal for message signal M of t is given by this equation that we all know, cosine omega c plus kf A of t, where A of t is the integration of the message in frequency modulation. If M of t has bandwidth 2b, then A of t also has bandwidth of 2b. The integration of the message also remains the same bandwidth. Then what's the bandwidth of this? The whole modulated signal. In general, for any message signal, it's really tough and difficult to find the bandwidth exactly. Sometimes there are no explicit solution. But for sinusoidal, luckily, we can analyze that and find the bandwidth approximately. In practice, the bandwidth is affected by the following factors. Signal bandwidth, which is 2b in this case, because the bandwidth of our message is 2b, and FM deviation frequency. Now the deviation frequency, FM deviation delta F, is actually can be found by the peak of the message signal. You know, this MP, this is the peak of the message signal. So let's say you have a message like this. So you say this is my MP, this MP, the peak. And Kf is constant related to frequency modulation over 2 pi. And this leads to Carson's rule. The total bandwidth of frequency modulation for a sinusoidal signal is almost equal to 2b plus 2 delta f, where delta f is the deviation frequency and 2b is the signal bandwidth of the message. Yes? So what's the difference here between wideband and narrowband? The difference is that wideband has bandwidth equal to 2b plus 2 delta f, while narrowband has bandwidth equal to 2b only. So wideband has larger bandwidth, and this bandwidth depends on the amplitude of the signal, MP. Yes? M peak, yeah, this one depends on it. As it gets larger, the deviation gets larger, and therefore the total bandwidth gets larger. This is very critical point to always remember. Now let's give graphical representation of what we are talking about. So you have in the first figure, you have your message signal, M of t, and the maximum amplitude, as you can see, is MP here. Here, this is the maximum amplitude, and we denote it MP, and this is the minimum, minus MP. So if I ask you find the frequency spectrum of this, the shape of the signal in the frequency domain, let's say that you can, it has this shape, and it's bounded between minus b to b with bandwidth 2b. If I ask you integrate it, because I need to use it for frequency modulation, you integrate it and you find that the shape changes to something like this, and the bandwidth remains the same. Now, modulated using FM modulation, and in general, you don't have that condition that alpha multiplied by A of t multiplied by k of is much smaller than 1. We don't have this condition. That condition for narrowband. We find out that the bandwidth looks like this, the total bandwidth of the FM modulated signal, which is equal to 2 delta f plus 2b, which is significantly large, where delta f is equal to kfmp over 2 pi, and A of t is the integration of the message. So this is the single important information I want you to know about this. That when you use wideband frequency modulation, the bandwidth gets larger by the deviation frequency, delta f, which depends on the peak of the signal, of the message signal. So if I give you two message signal, one looks like this, and another one looks like this, and tells you which signal would have larger bandwidth. You tell me this one. Why? If we are using the same parameters, and then what determines which bandwidth is larger is the amplitude of the signal, the maximum amplitude of the signal. So let's say both signals have the same bandwidth, 2b. So in that case, what determines which bandwidth is larger is only the signal amplitude. So this is important point to consider while you are dealing with amplitude, with frequency modulation. Now let's take an example for the case of tone, which is sinusoidal signal. Spectral analysis of FM is difficult for general signals, any signal. It's not possible sometimes because of the complication of the power series analysis. Now for the case when we have sinusoidal input where m of t is cosine omega mt, and I ask you that what's the bandwidth of cosine omega mt? Yes, the bandwidth. The bandwidth is basically FM. Yes, from where you know the bandwidth, you basically, this is this omega m 2 by Fm. The bandwidth of the signal is Fm. Omega m over 2 pi, which is Fm. A of t is the integration of the message. When you integrate cosine, what do you get? Sine omega mt over omega m from calculus. If you derive sine, you get cosine. If you integrate cosine, you get sine. And then what's the final formula for frequency modulation? If you are asked to write it, you tell me it's A exponential j omega ct plus kf multiplied by at. A of t. What's A of t is this. This is the one. You put it. And you write it in exponential term, and you say this is also equal to this format. Now, B in this case, I define B. B in this case is equal to kf over omega m, and we call this frequency deviation ratio or FM modulation index. Since this value is periodic, it's basically cosine beta sine omega mt plus j sine, and we know cosine and sine are periodic, then this whole function is periodic with the frequency omega m. Then we can write this whole function, we can write it in terms of new types of functions which are defined in the literature. We call them Bessel function, J n of b, or you call this variable sometimes beta or b, whatever. Let's call it beta from now on. So it's basically related to Bessel function. Jn is Bessel function, and this Bessel function is, you can neglect it if the value of n is greater than p plus 1 or beta plus 1. Beta plus 1. So basically, let's draw this function and see what's the shape of this function. This is the function, Bessel function. When beta is equal 1, the function shape is something like this. When beta equal 2, the shape changes. When beta equal 6, for example, this. When beta equals 6, you get this function. So the value, the shape of the Bessel function depends on beta. Yes? And beta depends on the frequency of the message signal omega n and kf, the frequency factor. And based on the frequency, you determine which Bessel function shape you will need to put in the equation to represent your FM modulated signal. So this is basically wideband frequency modulation and the differences from narrowband frequency modulation in terms of mathematical modeling and in terms of bandwidth and power and in terms of analysis as well. So frequency range for FM currently in currently employed and used FM application, it ranges from 88 to 108 megahertz. So you basically have around 20 megahertz of spectrum. Yes, 20 megahertz of spectrum. They are divided, these 20 megahertz of spectrum, into channels with bandwidth equal to 200 kilohertz. Each channel 200 kilohertz. Now divide 20 mega to 0.2 mega. How many channels you get? Yes, if I ask you the total bandwidth assigned for FM modulation is between this and this number. When you subtract them from each other, you find out that the bandwidth is 20 megahertz. And I tell you, in frequency modulation, each single channel has bandwidth equal to 200 kilohertz. How many channels I can have? How many FM station I can deploy? You tell me you divide this total bandwidth over this 200 megahertz over 220 megahertz over 200 kilohertz. 200 kilohertz is equal to 0.2 mega. So you divide 200 over 0.2. So you get what? You get 100. Why? Because this is kind of 200 over 2. 2 over 2 goes and remains 100. So this is from where 100 channel comes. Channel center frequency, you have this center frequency 0.1, 0.3, odd number. Frequency deviation is around this number, plus or minus 75 kilohertz. And signal bandwidth, for example, for audio application, we require plus minus 20 kilohertz. So there are plenty of bandwidth available for other applications like music, stock market quotations, interactive games, and some other applications as well. So basically, everybody should know this information as they are frequently used in practical and real life, and know that each FM bandwidth, each FM channel has bandwidth of 200 kilohertz, and if you divide the total bandwidth assigned for FM over the bandwidth of each channel, you get the number of channels you can have in your system. So for narrowband signal, this is kind of repetition. We have this condition satisfied, which leads to this condition as well, and you have for frequency modulation, you have this formula. You have A of t, which is the integration of the message, and for phase modulation you have directly M of t, and you can represent these formulas by using block diagrams, as you can see here. For example, for narrowband phase modulation, this equation, you can get it by this block diagram, and we call this phase modulation. You have your message signal M of t, you multiply it by sine omega ct minus, this is minus, and a, this is a, and you have cosine omega c multiplied by a, this is carrier generator oscillator, a cosine omega c, and then you sum them to each other, you get the narrowband FM. So the formula you get here is this. For frequency modulation, the first step you need to do is when you have your M of t, you integrate it to get A of t. A of t is the integration of the message. Then you multiply it by minus A sine omega ct, and you have oscillator here generates A omega ct, which is this, and then you sum them with each other and you get at the output narrowband FM modulated signal. So simple, so easy, just converted the equations into block diagrams. Now in practice, this modulation will not be very perfect, and there will be some amplitude modulation remaining because of imperfections in the hardware. The amplitude of your carrier will fluctuate a little bit and change based on the message signal. To avoid that, because we are not using amplitude modulation, we don't want any change in the amplitude. To avoid that, we use, after the modulation block diagram, we use limiter. This limiter determines the amplitude into two values, just no more. If it is above this value, it is below this value. And then to remove the unwanted interference and unwanted harmonics, we use band pass filter. So basically, this is why we use limiter to fix the amplitude of the modulated signal. We don't want any changes in the amplitude of the modulated signal. And the input-output diagram for an ideal hard limiter is this. If the message signal or the voltage greater than 0, make it +1. If it is below 0, make it -1. And this can be drawn in this figure. And you can implement it using, you can implement this function using operational amplifier. Operational amplifier, op-amp. This we call it op-amp, with back-to-back Zener diodes to limit the output amplitude. This feedback in order to limit the amplitude. Input to the band-pass limiter. The input is basically your modulated signal, A of t cosine theta of t, where theta of t has this information. It has the message information in it. A of t is constant, but it may vary slowly. To avoid this variation, we use the limiter. We assume A of t greater than 0, and we use this formula. If cosine theta greater than 1, we put it +1. If it is less than 1, -1. And this formula is basically periodic in theta with period 2 pi. And if you find the Fourier series, you will find out that omega naught of theta can be written in this form. And you just substitute the values instead of each other. You end up getting this total, this final formula. I don't want you to get into the details of this, but I just want you to learn that we use limiter in order to avoid the amplitude variation. And the way we use it, we just limit the amplitude here. We define a function that limits it to certain value. We don't want A to change with time. We want A to be constant. That's why we are using the the limiter. And then we pass this signal to band pass filter to eliminate all the unwanted signal. Also, we use for wideband frequency modulation, we use voltage controlled oscillator to generate a signal whose instantaneous frequency is proportional to an input. Yeah, voltage controlled oscillator generates a signal with instantaneous frequency proportional to the message signal. So the instantaneous frequency here is equal omega c plus kfm of t. This signal is band pass filtered, then used in a modulator. VCO can be constructed by using input voltage to control one or more circuit parameters. VCO depends on these parameters actually. RLC. In all cases, feedback is used to adjust the frequency. So think of voltage controlled oscillator as a modulator. Yes, because it changes the instantaneous frequency based on the message signal. And what does frequency modulation do, or phase modulation? Change the frequency of the modulated signal based on the message signal, M of t. So basically this is similar like to frequency modulation, and this is the circuit that you can use in order to produce that voltage controlled oscillator. And this is basically, you think of it as an FM modulator as well, because it changes the frequency based on the input. This is the electronic circuit that you can basically design this. You can fabricate this. You can buy these resistors and this transistor, this capacitor, solder them with each. You can just connect them with each other on a whiteboard or PCB board, and you will have connect them with an antenna, and you will have an FM transmitter. So now you can go home if you want and build an FM transmitter. You can send your audio, your message signal to 10 kilometer away from you or what, and you listen it from your radio. You know this at certain frequency. You just build this circuit and connect it here to your audio, your voice, your video, the music you want people to listen to or whatever. And here there is an antenna, and you built an FM station here. and go to your mobile application and open FM radio and tune it to the frequency you are using, and you get your message. Even if you are far away 10 kilometer or whatever, this is a way to send your information without using the internet. Or kind of you are using it for communication. So basically at the end of the day, you can use it for internet purposes as well. So you understand me, but the problem here, it's like streaming, one-way communication. You don't have any interaction in the uplink. You just, whatever this circuit puts as an input, you get at your at the receiver side. Is that beautiful? That now in this lesson you learned how to design an FM station, the ones who are broadcasting FM radio and this, you're now able to design it. You just need to go to maybe Google or some books and search FM circuit modulators, and there are hundreds of maybe pages and websites and material on that that can teach you how to build that circuit, and then one day you can have your modulator. I don't know, you might have some maybe applications that require this. Currently, it's very common to analyze the FM waveform digitally, either at an intermediate frequency and then mix it up to the desired carrier, or to directly synthesize the waveform at the carrier frequency. This circuit is analog, but basically you can also design it in digital. You know, if you have my software-defined radio or USRB device, as the ones you have seen maybe in the communication lab, you can build your FM transmitter by software, you know, LabVIEW or MATLAB. You can write the code there and get the signal and generate it, and just send it to the hardware of the USRB, and then you have your FM signal on the air. So this is FM, direct digital synthesis, and this is intermediate frequency, and you get your frequency modulated signal. So basically, it's not difficult to build an FM transmitter. It's super easy. I remember when I was in my undergrad and when we took this course called Introduction to Communication, one of the homeworks of the assignments was to build an FM transmitter. So we built it, and we had at that time FM station, and we received the data we are transmitting from that tiny circuit in our phones, and we listened to radio, audio. It was really very nice experience. So if you want to do it, you can also do it. You can integrate it with your project, Internet of Things project, if it requires FM station for transmitting your data, sending it for long ranges. I don't know, it might, your Internet of Things application might record something, yes, and you want this to be transmitted for public. Like you recorded this, there are some important news, and you want, when this important news comes in, you just need to spread it to all the people in certain to all the people who are interested in this information in certain location, let's say Antalya. So it's kind of super easy to build that as well. Or you can also, I mean, either you can build it in analog or digital. I prefer digital, it's super easy. But in digital, you need to utilize the microcontroller capabilities in this case, and maybe you won't be able to use it with ESP. ESP cannot make it. I don't think you can modulate if you can send an FM signal or generate using ESP. You need USRB, software-defined radio, or you can, if you don't have enough money to buy software-defined radio or USRB, you can basically build this simple circuit. This doesn't cost you more than 20 Turkish lira, 20 or 30 at maximum, and you have a FM station with very high quality audio. So with this, we finish our lecture and conclude it and stop here. And thank you very much for your attention and for your listening. And we meet in next time, hopefully. Thank you very much and see you next time. See you.